I'm going to start off by talking about magnetic contrast agents for improved characterization of hydraulic frac jobs and also for downhole permeability and its anisotropy. In particular, looking at the properties of these particles compared to the intrinsic properties of the reservoir rocks and fluids, and also the importance of taking account of the reservoir conditions, in particular the reservoir temperatures. I'll also be briefly talking about characterizing natural nanoparticles. There are natural small fine particles in the reservoir that have an important effect in controlling permeability. And to finish off, I'll talk about quantifying fines transport of nanoparticles during things like water injection, and also quantifying pipeline corrosion. So to start off looking at nanoparticle contrast agents, this is a very simple schematic. What we're intending to do is inject fine nanoparticles along with proppant to get a better idea of where the fractures have occurred in hydraulic frac jobs. And I'm working on this in collaboration with a group at Rice University, and they've been producing the nano-sized particles, and I've been doing the magnetic characterizations, and we've also been working on some potential sensors. For these particular nanoparticle contrast agents, you need to have sufficient magnetic susceptibility contrast between the nanoparticles and the reservoir rocks and fluids. And they also need to be stable at reservoir conditions, particularly reservoir temperatures. The effect of pressure doesn't have as much effect. And the delivery of these nanoparticles should be aligned with present-day pumping into the reservoir, such as during the frac job. Now, to give you some idea of the susceptibility contrast between these particles and the intrinsic properties of the reservoir, these particles have extremely high magnetic susceptibility. This is the susceptibility at room temperature. I'll shortly be showing some graphs at reservoir conditions. And to compare, these are some of the typical minerals in your reservoir under the same units. So your quartz, if you're in a clastic reservoir, or calcite in a carbonate reservoir, these have very, very low magnetic susceptibility. They're what's termed diamagnetic. They have very low and negative susceptibility. Also, most of the reservoir fluids are diamagnetic as well, formation water and the crude oil, and also some of the clays like kaolinite. Some of the other permeability controlling clays like illite and chlorite, they have positive magnetic susceptibility and they're paramagnetic. Even they have extremely low magnetic susceptibility compared to these nanoparticles. So the nanoparticles have extremely high magnetic susceptibility in comparison. And you would only need something like a 1% mass concentration of these nanoparticles mixed with proppant in order to be able to sense these things. Now we can actually model the effect of the temperature conditions, the reservoir temperatures on these nanoparticles using a large bit of kit that we have. This is essentially a large electromagnet where we can look at the magnetic properties and create hysteresis loops. But we can also do this at temperature, so we can actually simulate the effect of reservoir temperatures. And here are some results. So this is one of the nanoparticles, and this blue curve here are the results at room temperature, and the particles look very good at room temperature. However, if you heat them up and go to fairly moderate reservoir temperatures, 89 degrees here, 125 degrees, a lot of their magnetic properties, the susceptibility goes down. The susceptibility here is actually the slope of the graph at any point, okay? So these are hysteresis curves, and the slope is at any point is the susceptibility. So these particles are good at room temperature, but not so good at reservoir temperatures. These particles, on the other hand, are much, much better at reservoir temperatures. You can see that all the graphs are relatively similar. There's a bit of change at reservoir temperatures, but these are much, much better at reservoir conditions. So in collaboration with the group at Rice, we're looking to get nanoparticles that don't lose much of their magnetic properties at reservoir conditions. Incidentally, you're going to see a good talk this afternoon by Brett Chandler, and this type of equipment could actually be used to help monitor some of the things that he's looking at. He's looking at nanoparticle lubricants, and it's very important to know when these lubricants oxidize, for instance, and you could use this type of kit to actually sensitively monitor when the lubricants are about to oxidize and so forth. So just advertising his talk this afternoon. Just to give you a very brief idea of natural nanoparticles, in some tight gas reservoirs we see very fine particles, for instance, of hematite. These wider loops here are due to hematite in the red sandstones. You don't get any hematite in the white sandstones, and in the white sandstones the permeability is just controlled by illite. And what we find is the slope of the magnetic hysteresis curve is related to the actual permeability of the rock. So the higher the slope, the greater the amount of illite, the lower the permeability. If we have samples over here with exactly the same amount of illite, the same high field slope, but a little bit of hematite, then we find that the permeability actually goes down. And that permeability goes down because of these very fine nano-sized particles of hematite. And we can actually quantify this and the relative roles of hematite and illite on the permeability using this type of analysis. Another main area that we're looking at is fines transport, and we can actually model this in the laboratory. Here's a flow cell, and we can actually model the magnetic properties in the laboratory. So this is just an example of a core flood, 2 cores here, and these are the magnetic properties before the core flooding. And what happens after the core flood is that the magnetic susceptibility goes down. And in this case, this is due to flushing out of these nanoparticles in the core. So we can sensitively monitor this fines migration using these magnetic techniques. Another application could be to pipelines. These are some images of filter papers where they've collected the fines. This is at the manifold in a pipeline. And they couldn't actually use X-ray diffraction to sensitively quantify these fines, but we managed to do this using our magnetic techniques. So this again is a series of hysteresis curves. The virgin filter paper is this blue curve here, and the other 2 curves are due to the fine particles collected on the filter paper at a filter cartridge. So this curve here is at the inlet end, and this is at the outlet. And you can see that the filter cartridge is pretty efficient. There's a lot fewer particles at the outlet, so the filter cartridge is quite efficient. And we can actually get some idea of the types of particles here. We know that, for instance, there's a little bit of paramagnetic fines here, and because of this kink in the curve here, we know we've got some ferrimagnetic fines, maybe some iron oxides. This was in a fiberglass pipeline, so the particles so far had only traveled through a fiberglass pipeline. This gives an example of particles that have gone through a steel pipeline. They needed higher pressures as they were injecting close to the formation, and they didn't think at first that this steel pipeline was eroding much. But in fact, what you see here is an enormous signal due to very fine ferrimagnetic particles that are corroding from this steel pipeline. And we can sensitively measure these things. So that's just to give an idea of how sensitive this kind of technique is. The other lines on here are other results further up the injection line when the particles had only gone through the fiberglass pipeline. So just to summarize these three main areas, we've been looking at magnetic contrast agents for improving our characterization of frac jobs. We could also use this for looking at the intrinsic permeability and permeability anisotropy if we merely injected these particles into the formation rather than injecting them along with propant. We've been looking at the natural characterization of nanoparticles, which turns out to be extremely important in unconventional as well as conventional reservoirs and in tight gas reservoirs. And we've also been looking at this fines transport, for instance, in water injection, and also associated with pipeline corrosion. Thank you very much.